Hi, my name is Donatiano. I am a PhD student at Lyon One University, and today I will present my paper entitled Feature-Driven Time Series Clustering, joint work with Angela Bonifati and Raymond Gur. FTS is a semi-supervised algorithm that uses the feature extracted from the time series in order to cluster them. To the best of our knowledge, FTS is the first feature-based semi-supervised clustering framework with these key properties. FTS is based on clustering by seeding concept. The idea is to create two kinds of connection between the data of the dataset called must link and cannot link. With the must link, we are defining a constraint of belonging between two data. It means that two data points should be clustered together. By opposite, the cannot link defines a non-belonging constraint, hence going to separate the data points. Seeded k-means is the most prominent algorithm of this category. We also compare FTS against the state-of-the-art of the unsupervised time series clustering called K-shape. K-shape computes the most representative time series in a given cluster and insert in that cluster all the time series that are similar to the most representative one. The main problem of K-shape is that it assigns spurious time series to cluster and it does not deal with the time series of different length. In this figure, we can see the 5 main steps of our algorithm. The first step is the extraction of the features. Indeed, using a library called tsfresh, we can extract numerous features. So, as indicated in the figure, we can extract plenty of features completely different. And among all the features extracted, only some of them are really useful in order to obtain a good performance. Therefore, we need a method that permits to discriminate which features have the best correlation with the dataset. The operation of discrimination of the features is done via a procedure called Benjamin and Iacutelli procedure. This procedure needs a small subset of supervised data in order to compute the p-value for each feature, useful for considering the importance of each of them. In the figure, we can see how the quantile feature is the most discriminative according to the Benjamin and Iacutelli procedure. However, this procedure doesn't let isolate the number of features useful for the clustering. Therefore, in order to obtain the optimal subset of features, FTS adopts an algorithm called Principal Features Analysis. PFA computes the explained variance of each features and, based on a set threshold, select the minimum number of features that need to obtain the threshold requested. In the figure, we can see that fixing a threshold equal to 90% of the explained variance, this can already be obtained with the first 3 features on the left-hand table. Therefore, only the first 3 features will be used by the algorithm from now on. Once we select the features, we convert the time series and the relationship into edge-weighted graphs. The encoding of the time series into edge-weighted graphs allows us to capture the global relationship among the raw time series samples. Therefore, we convert each time series in an edge-weighted graph where the vertices represent the time series while the edge represents the distance between the connected of the edge, i.e. the difference between the values of the features of the two different time series. In the figure, we can see that the weight between V1 and V2 is 14 because of the difference between the quantile features of time series 1 and time series 2. In order to capture the similarity, we only retain in the graphs the edge whose weights are less than a given threshold distance. Therefore, once ordered in ascending way all the distance and select a threshold, FTS cuts all the edge with the distance higher than a maximum fixed. In the figure, we decide to keep the 50% of the edge, so all the edge with a distance higher than with 28 will be removed from the graph. Finally, once pruned the graph, we will apply an algorithm of community detection in order to extract the communities from the graph. FTS applies this routine on all the graphs obtained by the features. Therefore, we need a structure to combine all the results obtained in one single data structure. FTS uses a structure called co-occurrence matrix to combine all the communities in one single structure. The co-occurrence matrix is a matrix where the columns and the rows represent all the time series of the dataset, and each cell represents a similarity value between these time series. The similarity of the two time series increases with the number of times that two time series are clustered together. In order to make more robust the computation of the similarity, each feature has weights that depend by the number of community found by the community detection algorithm. The weight will be computed dividing the number of community of the features by the number of requested cluster if the number of community is higher than the number of clusters. Vice versa, if the number of clusters requested is higher than the number of communities extracted, we invert the numerator and denominator of the function. The weight is equal to 1 in case the two values are equal. As an example, here we show the weights of the three chosen features corresponding to the number of community found in each graph encoding of the respective features. Indeed, the algorithm for community detection finds for the trend STDR error 3 different community. In this case, we have divided 2 by the number of extracted community, i.e. 3. In the other feature, called trend value, one only community is found. Thus, we divided 1 by 2. Once we have computed the co-occurrence matrix, we can apply the k-methodic clustering algorithm on the matrix in order to extract the corresponding clusters. In order to evaluate the performance of our algorithm, we first used the dataset of the UCR collection. This collection consists of about 64 datasets. In the figure, we show an excerpt of the results obtained on the datasets. We can see how the results obtained by our algorithm, which are expressed through the adjusted middle information, exceed those of the seeded k-means used as a baseline and k-shape for the majority of the dataset at hand. The second dataset is a real dataset that was provided to us by the Georges Pompidou Hospital in Paris. The latter consists of patients who suffer from kidney disease and for whom we need to predict whether they need dialysis or not. We have two variants of datasets, whose differences lie in the number of patients per dataset and the length of the measurement. We can see how the result obtained by our algorithm outperforms those of the seeded k-means. We can test k-shape on this dataset because it contains time series with different length, and k-shape doesn't deal with this kind of dataset. Finally, we tested the scalability in terms of time of VTS, increasing the size of the dataset with the fixed length of the time series and increasing the length of the time series but leaving the same number of time series. We can see how, if we increase the number of time series, the time, expressed in logarithmic scale, will increase. Moreover, we can see that the majority of the time is spent for creation of the co-occurrence matrix. The situation is somehow opposite when we increase the length of the time series. In that case, most of the time is spent to extract the features from the time series. In this presentation, we have presented VTS, a system capable of doing time series clustering while leveraging custom features for each dataset that best fit the dataset itself. This overcomes the result in the state-of-the-art algorithm on raw data or on a fixed set of features. VTS will be demonstrated at the SIGMO 2021, so please stay tuned. In the next future, we plan to make the pipeline completely unsupervised, and we also want to be able to set a dynamic threshold to be used in the graph encoding. Finally, we are evaluating if the use of relevant weights extracted from the supervised procedure can be used in combination with the current weights. Thanks a lot for your attention.